Hi, I'm presenting randomness and fairness in two-sided matching with limited interviews. My name is Hedyeh Beyhaghi. I'm a postdoc at ITCS, and this is a joint work with Tardos. In this paper, we study matching markets where both sides of the matching have limitations. On one side, we have applicants who, although find a lot of the job positions on the other side desirable, can only apply to a limited number of them. This could be because the system has imposed this limit, or since the applications are time-consuming and costly, they can only apply to a limited number. And on the other side, we have the job positions that need to run an interview process before hiring applicants. And again, since the interview process is time-consuming and costly, they can only interview a limited number of their applicants. Our goal in this paper is to study the effect of these limitations on the matching, and more particularly the size of the matching. Traditionally, the matching algorithms did not consider these kinds of limitations into account. For example, the deferred acceptance algorithm by Gale and Shapley that finds a stable matching assumes that participants can consider as many options as they want. In the more recent years, there have been more work on matching with limitations, and here there's a subset of them. But as you see, there have been very few works on where there's limitation on both sides of the matching, and they either consider different settings or different objectives. Okay, let me define our model more formally. We have n applicants and n positions. We show applicants by circles and the positions by squares. We focus on the case where the preferences of each participant over the other side comes independently and uniformly at random, which kind of means that each position or each applicant is equally popular. This assumption makes our analysis tractable, and also we see interesting facts even in this simple case. We run a three-stage matching mechanism. In the first stage, each applicant applies to k positions. In this picture, k equals 2. And right next to each position, we see the applications that they have received. In the second stage, the positions accept k prime of their applications for interviews and make interview offers to them, and reject the rest. Here, k prime is also equal to 2. So this position accepts the orange and blue applications, but rejects the green application. Then we run the interview process, and each participant refines their preferences. And after that, we run the applicant proposing deferred acceptance algorithm. We're going to assume that at each stage, the participants choose their favorite options. This makes sense because of the independent and uniform preferences. This means that in the first stage, each applicant is applying to their k favorite positions, and the positions are accepting their k prime favorite applications and reject the rest. And this is a truthful Bayes-Nash equilibrium in this setting. Finally, we consider the large market setting, which is a standard assumption in matching papers. It means that we keep k and k prime constant while we study the case where n approaches infinity. And the large market setting makes sense because if we had a small market, limitations didn't really make sense. The problem that we're going to study from here on is finding the expected size of the matching, or the fraction of matched participants, as a function of k and k prime, the limit on the number of applications and the limit on the number of interviews. Okay, now let's focus on the case where we have a limit of 1 on the number of interviews. Our first observation in this case is that the matching mechanism becomes much simpler. So after the applicants apply to the positions and the positions accept only one application, we don't actually need to run the deferred acceptance algorithm. Basically, each applicant that receives an interview offer is going to be matched finally. I should mention that in this case, we don't really have the interview process, but we're still calling the acceptance of applications an interview offer, just to be consistent throughout the talk. Now let's solve the easy case where both the limit on the number of applications and on the number of interviews is 1. Each applicant is applying to one position. So in total, we're going to have n applications. And remember from our model that all the preferences are independent. So we have n independent applications sent uniformly and independently to the positions. So it's easy to find the probability that a position receives an application. It's actually a simple balls and bins analysis. And when n goes to infinity, this approaches 1 minus 1 over e. In this case, since each applicant has only one application, they are going to receive at most one interview offer. So they're going to accept it anyway. And the number of positions that receive an application is going to be the same as the number of applicants that are matched. Okay. Now let's get back to the more general case of arbitrary number of applications and a single interview offer. It took us some time to realize that this also has a very simple solution, and it's going to fit on one slide. Our first insight is that when n approaches infinity, we may assume that the applications are independent. So technically, with a finite n, different applications of a single applicant are not independent. They are going to k distinct positions. But as n goes to infinity, even if we draw a fresh sample from the uniform distribution, the probability that this is going to be the same position as the k minus 1 other application tends to 0. So in the limit, we may assume that all applications of a single applicant are independent. Previously, we knew that the applications of different applicants are also independent. So basically, we have n times k applications that are sent independently and uniformly at random to the positions. As a side note, this is kind of like a new variation of the balls and bins problem. So the balls here are the applicants, and we can think that there are multiple copies of each ball. And these are all sent independently and uniformly to the bins, and the bins have capacity of 1. And for example, the problem that you're studying here is the number of distinct balls that fit into the bins. Okay, back to our problem. So with n times k and applications sent independently to the positions, we can find the probability of an application being accepted. So by definition, it's going to be the total number of accepted applications over the total number of applications. Okay. And there is a 1-to-1 correspondence between the accepted applications and the positions that have received any application, because each position that receives any application is going to exactly accept one application. All right. And we can find the number of, or the expected number of positions with applications pretty easily, similar to our analysis on the last slide. So with nk applications, this is going to be the probability that a position receives any application. So this times n is the number of positions with applications, and the total number of applications is n times k. All right. So now from a random applicant's point of view, each of their applications have the same probability p of being accepted. Therefore, the probability that an applicant receives any interview offer is going to be 1 minus 1 minus p to the k, and we are substituting p from here, so we get this number. And from 2 slides ago, we know that the size of the matching in this case is the number of applicants that have any accepted applications. All right. So let's see what this function looks like as a function of k. All right. Okay. So we have this diagram. Here, the x-axis is k, the number of applications, and the y-axis is the size of the matching, or the fraction of matched agents. As you see, as we increase the number of applications, first the size of the matching is going to increase, and then it's going to decrease. So this is the first interesting fact that we see. The size of the matching is not monotone in the number of the applications. Okay. So at 1, we have the around 63% that we saw on the last slide, 1 minus 1 over E. And you may find it interesting that this curve converges to 1 minus 1 over E at the end, which is equal to the value of a single application. Okay. So based on the formula, we know that the shape looks like this, but what is the main reason that it's not monotone? We find out that having more applications have both a positive and a negative effect. The positive effect is that with more applications, the number of positions that have received any application increases. So with only one application, only 63% of the positions have received some application. But as we increase this number, you see that it grows up pretty fast. The negative effect is that since the applicants are applying to multiple places, the probability of an accepted application belonging to somebody who has already other accepted application goes high. So we will have a bunch of people who have received multiple applications while the rest have received 0. So we see that after we have 3 applications, the negative effect takes over and we will have a decreasing size of matching. Okay, so the next question that we want to study is that, is there any hope of getting a larger size matching if we have a different distribution of the number of applications? Or basically, what happens if the applicants can apply to different number of positions? They don't have to all apply to K positions. Okay, so this lemma here tells us that if some applicant applies to X positions and another applicant applies to Y positions, while the difference between these numbers is at least 2, we can redistribute these applications and make their number of applications closer to each other and increase the size of the matching. And the proof is actually straightforward. All right, so it has a simple corollary that says that given any average number of applications X, the size of the matching is maximized if the applicants either apply to floor X number of positions or ceiling X number of positions. Basically, applying to the same number of positions or 2 consecutive numbers is the best way of distributing the applications. Okay, so let's see what is the size of the matching in this case. All right, so we have X as the average number of applications. And we're going to have this fraction of people applying to floor X applications and this fraction applying to ceiling X application. And the probability of the applicants being matched is similar to the solution from the previous slides. And we can also find P similar to before. All right. Now let's see the shape of this figure. Okay. So again, on the x-axis, we have the average number of applications, and the y-axis is the size of the matching or fraction of matched agents. And for example, at 2.5, half of the applicants are applying to 2 positions, while the second half are applying to 3 positions. Okay, so here we see our second interesting fact, the U-shape between the 2 integers. So what is basically happening is that if we start from, so first of all, it means that having all the applicants apply to 3 positions is the best, even if we're allowed to pick other distributions of applications. So 3 applications is still optimal. And when we have a limited number of interviews, we need to also limit the number of applications to have a good size of matching. And secondly, the maximum matching is achieved with a fair system of allocating the applicants. For example, If we're here at 3 applications, if we allow a group of people, if we favor a group of people and let them apply to one more position, the size of the matching decreases. Also, if we discriminate against a group of people and let them apply to one less position, the size of the matching decreases. And the local maxima of this figure are going to be the integer values. We call this scallop-shaped figure. So basically, when people apply to the same number of positions, we get the maximum size matchings. Okay, so far we understand completely what happens with a single interview case. Now let's move on to multiple interviews. So when we are in the multiple interview case, for example, when the positions accept 2 of their applications, we really need to actually run the deferred acceptance algorithm. So the solution for this case is going to be much more technical, although the solution is still clean, but I won't get to talk about that in the talk. And please check out the paper if you're curious about this analysis. But at the end of the day, we managed to find the expected size of the matching, even with the more complicated deferred acceptance algorithm. And we come up with the size of the matching. All right, so here the x-axis is again the average number of applications. The y-axis is the size of the matching, or the fraction of matched participants. We see the curve that we saw previously for k equals 1 here. And here we have the curve for k prime equals 1. Here we have the curve for k prime equals 2, 3, and so on. So as you see, still are 2 weird facts. The non-monotonicity in the number of applications and also the U-shape between the 2 consecutive integers happens here, but to a lesser degree. Before we finish, I want to emphasize that these weird behaviors are a consequence of limiting the number of interviews. If we don't have any limit on the number of interviews, the matching size is going to be monotonically increasing. And actually, it's not. So on the right-hand side, you see the size of the matching when we have no limit on the number of interviews, and the x-axis is the average number of applications. And it's actually not hard to prove this theoretically. Basically, we're running the deferred acceptance algorithm, and with more applications, it's like we're appending the lists. So with these longer lists, with these longer preference lists, we definitely come up with a larger size matchings. Okay, let me conclude. Our main technical contributions are: 1, computing the expected size of the matching as a result of the deferred acceptance algorithm as a function of the limit on the number of applications and interviews. And 2, we find the optimal way of distributing the applications when given a fixed average number of applications. Our work suggests 2 policy recommendations. First is that if there is a limited ability in granting interviews, we need to limit the number of applications, and sometimes we need to severely limit the number of applications that the applicants can send in order to achieve a larger size matching. And the second is that the optimal matching size is achieved by a fair system where all the applicants apply to the same number of positions. I would like to mention 2 open problems. The first one is relaxing that the preferences come from uniform distributions. Maybe that's the main step to make the model more realistic. So fortunately, there have been some work on correlated distributions, but the usual assumption is that the preferences of the applicants or the preferences of the positions are almost identical. So our work is kind of the other extreme case where the preferences are completely random, but it would be nice to have some results in the between. And the second open problem is to study other matching mechanisms other than the deferred acceptance algorithm. So we still have the same first stage, but we're changing the matching mechanism and to compare these different mechanisms. That's all. Thank you so much for watching.